My dear students, in the previous video, we have started to solve the problems in the exercise 12.1. In that exercise, I have solved first three problems in the previous video. Now I am going to start the fourth problem in the exercise 12.1. Exercise 12.1, fourth problem. Star is defined on a set, a binary operation star is defined on a set A equal to the set of all elements A plus 5 root 5 B. Set of all elements of the form A plus root 5 into B, such that A comma B belong to the set of integers. The set A, the star is a binary operation dependent on this set. We have to check whether the star is binary on A. That is the problem. Check whether the star is binary on A. That means if you consider any two elements in the set A, after operating the operation star, the resulting element is also in the set A. We have to prove. If it is so, then we can say star is binary on the set A. Now let us consider two elements. Consider A plus root 5B, comma B C plus root 5 into D in the set A. I am considering two elements A plus root 5 into B, C plus root 5 into D in the set A. With usual multiplication, this is star is called usual multiplication. Usual multiplication. That is A plus root 5 into B into C plus root 5 into D equal to A into C, AC, A into root 5B, that is root 5 into AD, plus root 5 into BC, A into C, AC, A into root 5 D is root 5 AD, similarly root 5B into C, root 5 BC, root 5 into root 5. Last term is 5, root 5 into root 5 is 5 BD. 5 BD. This is the product. Here you consider first and last term AC plus 5 BD. If you take root 5 common, you will get BC plus AD. So it is of the form A plus root 5B. A plus, see this up to this, AC plus 5BD plus root 5 into BC plus AD. See it is of the form A plus root 5D, A plus root 5B. This is again an element of the set A. Therefore, A is usual multiplication, and the usual multiplication A is closed. The usual multiplication, the set A is closed, or usual multiplication is binary on A. Therefore, usual multiplication is binary on A. The star is not defined here. In this problem, binary operation, usual multiplication. A binary operation, you study a binary operation, usual multiplication is defined on the set A, not star. Yes. Specifically, they are given usual multiplication. And we have to prove that this usual multiplication is binary on A. If you consider any two elements of the set A, the product is again an element of the set A, then we say that the set is closed under the operation usual multiplication. That is the problem 4. Next, problem 5. See, I request you one thing. When you see my videos, you keep your textbook with your side. Keep your textbook side by side and you refer the problems on the textbook. Because I am not writing the problems in detail in the video. Problems are in the textbook, you refer the problems and you see the solutions in the video. I am deriving the problem, you refer the solutions here and you take the problem from your textbook. That's why I'm asking you to keep the textbook with your side and see the problems in the textbook. Next, because I need not write entire problem in the blackboard, in the board. That is fifth problem, first subdivision. Here, binary operation star is defined, operation star is defined on a set of rational number. Set of rational number. A binary define here. Define an operation. Define an operation star on the set of rational numbers Q as follows. Such that for every A comma B belongs to the set of rational numbers Q, A star B equal to A plus B by 2. This is the rule for the operation star. For every A comma B belongs to the set of rational numbers Q, the operation A star B is again expressed as A plus B by 2. If it is the rule, we have to check first subdivision whether this operation is binary on Q and commutative property whether it is true and associative property. Examine the closure property, commutative property and associative property. Closure property is nothing but we have to prove this star is binary on A. If you prove this operation star is binary on Q, we can say that the set is closed under operation or closure property is satisfied. Okay, first closure property. Closure property. For all A comma B belongs to the set of rational numbers Q, the operation with star A star B equal to A plus B by 2. This A plus B by 2 is also a rational number. It is also belongs to the set of Q. Therefore, the operation of A and B with star A plus B by 2 is again a rational number. Therefore, star is binary on the set. Star is binary on the set of rational numbers Q. That is, Q is closure property is satisfied. Hence, closure property. Hence, closure property is satisfied. Satisfied in Q. Now, commutative property. Second one. Commutative property. Second property, commutative property. Second one, commutative property. For all A comma B belongs to the set of rational numbers Q, we know that A star B equal to A plus B by 2, the rule given, and this A plus B addition can be reverse addition is possible, therefore B plus A by 2. A plus B can be replaced by B plus A. By the rule of the star, B plus A by 2 is nothing but B star A. Therefore A star B equal to B star A. Therefore A star B equal to B star A, hence the commutative property. Hence the commutative property is true in a set of rational numbers Q. Again, now third property, associative property. Closure property is satisfied, commutative property is also satisfied. Third one is associative property. Associative property. Here we have to consider three elements in the set of rational numbers Q. For associative property, proving the associative property, we have to consider three elements. For every A comma B comma C belongs to the set of rational numbers Q, A star B equal to, then A star, associative property is A star B star C. A star B star C equal to A star B star C by definition B plus C by 2. It's again A star B. It's now again it is A star B. This is equal to A plus B by 2. That is A plus B is B plus C by 2, the whole divided by 2. This is again A star B. Therefore A plus B by 2. So considering the numerator, in the numerator 2 as the LCM of the numerator, 2 into A, 2A plus B plus C by the denominator 2. So the denominator of the numerator becomes in the denominator. It is equal to 2A plus B plus C by 2 into 4. You consider this is expression 1. This is A star B star C. Now A star B star C. We have A star B star C. In this case, A star B is A plus B by 2. A star B is A plus B by 2 star C. It's again A plus A star B. Like it is A and this is B. A star B. Again A star B is A plus B by 2 plus C by the whole derivative. By definition, A star B is A plus B by 2. It is again by taking LCM in the numerator as 2, A plus B. Clearly, we will write it clearly. That is equal to, if you take 2 in the numerator as LCM, A plus B plus 2 into C is 2C by 2. It is again equal to A plus B plus 2C by 4. This is your expression 2. See the left hand side A star B star C is 2A plus B plus C by 4. A star B star C is A plus B plus 2C by 4. These two are different. Now 1 and 2, left hand side is not equal to right hand side. from the expressions 1 and 2, from the expressions 1 and 2, we can say that 1 is not equal to 2. Therefore, from 1 and 2, A star B star C is not equal to A star B star C. Therefore, associative property is not true in Q. Therefore, associative property is not true in Q. Closure? True. Commutative property is also true, but the associative property is not true because left-hand side is not equal to right-hand side. Let's solve about three properties in the first subdivision of the fifth problem. Now, in the fifth problem, second subdivision, the same operation, binary operation with the same condition, A star B equal to A plus B by 2 in the set of rational numbers Q, we have to prove that the existence of identity and inverse. That is the second part of the problem 5. The existence of identity. Existence of identity. Suppose for every element A, belongs to Q, there exists an identity element. There exists an identity element E belongs to Q, such that A star E equal to A, because A is any element, E is identity, A star E equal to A by definition of identity. A star E equal to A because E is the identity. But what is A star E by rule? A plus E by 2 equal to A plus E by 2 equal to A. On cross multiplication, this is A plus E equal to 2A. From this, what is E? 2A, this plus A value bring it to the right hand side, it's minus A. 2A minus A is A. E equal to A. E is the identity element, only identity element, but A, it is equal to A. A is already an element of Q. E is identity. A is already an element of Q. Therefore, we are finding that two identities in the set Q. One is E and another is A. It is impossible. In a set, the identity element is unique. We have proved theorem. So, there are two identities we have. It is impossible. So, identity element of a set is unique. Therefore, existence of identity is not true. E equal to A is impossible. E equal to A is not possible because identity element is unique. Identity element is unique in a set. Identity element is unique in a set. In algebraic structure, whatever it may be, identity element is unique. So there are two identities we have. It is impossible. Therefore, identity property is not true in Q. Since identity is not true, we need not prove the existence of inverse. There is no question of inverse. If the existence of identity fails, certainly inverse is not possible. Therefore, existence of inverse is also not true. Since the identity Since identity is identity property, since the identity property is not true, we need not prove that. We need not prove the existence of the inverse. Existence of the inverse. So inverse property is also not true. Hence, inverse is also not satisfied. Hence the problem. And I will stop here. We will continue the sixth problem in the next video. Thank you.